Hi, my name is Haley Warren. I'm a part of the UAV team for the conservation of African painted dogs in Zimbabwe. We're a diverse group of mechanical, materials, and electrical engineering students working to obtain this goal. So our main objectives are going to be helping the Painted Dog Research Trust Fund with locating, tracking, and studying African painted dogs in Zimbabwe. The PDRT is located in Victoria Falls, Zimbabwe, and they're studying throughout the Zambezi River Valley. Unfortunately, the African painted dogs are actually becoming an endangered species. They used to inhabit about 39 countries throughout Africa, and unfortunately now only inhabit about 7 to 9. And their numbers went from about 500,000 down to just a few thousand within the last couple decades. So our main goal for this project is to develop a UAV which will fly about a 40-mile range, 80 miles total, take off and land in a 65-foot range, detect dog collars within 1.2 miles radius from them while in flight, haul the payload necessary for tracking those dogs, be electric powered, easily transportable to Zimbabwe, fly autonomously so researchers in Zimbabwe don't have to undergo extensive training on how to fly it, and it'll be nice and easy. And then also easy to maintain, repair, reproduce, so that if anything does go wrong, it can be fixed. And then also maintain a $3,000 to $5,000 budget, as this is a not-for-profit. So this project has actually been worked on for two previous semesters. The top left, you can see the plane that we were presented with at the beginning of the semester. Unfortunately, just due to some flaws, and we ended up scrapping that plane. The center of gravity was a little off. The gas power introduced some difficulties. It was also difficult to assemble and break down, so transportation issues, and then also just putting everything back together again up in Zimbabwe. And then also it had unreliable landing gear, which was not favorable for use in not optimized conditions in Zimbabwe. So this semester we did a progressive approach, and we went with a glider-based system with no landing gear and electric motor, have it be fairly sturdy but on the same side, have it also easy to repair. So it's easy to make new wings, easy to make a new tail. If anything does break, it can be fixed. And yeah.
So taking these new criteria, we wanted to make a simple plane. We wanted to make it as small as possible because the one we were given when we came into the semester was way too large. There's a bunch of empty space in there. It increased drag. So we wanted to make it as small as possible, as simple as possible, and as easily fixed as possible. So our first prototype was Mark 1 here. It's on the table. Taking this, we just wanted to do a proof of concept. So we did a glider test on it. Then we moved up to Mark 2, which was the first powered flight, tweaking a little bit each time. However, for our final model, which is the gray one on the table here, we decided to do a female mold, which is different than the other ones, so we laid up on the inside to get a nicer surface finish. We used a 3-part mold for the top and the bottom, just due to our limitations in the mill. We laid up 3 layers of fiberglass in there, birch plywood, bulkheads, and then vacuum bagged that. We then popped it out, sanded it, and put a layer of paint on it to make it look nice.
So the objective of the wing design is to make the wing as simple as possible, easy to manufacture, easy to maintain, and easily replaceable. We would also want the wing to be able to pop on and pop off easily, so it means that no electrical wirings running through the wings and no control surfaces such as ailerons. We've come a long way from designing wings from Mark 1 wing, which has a basic rectangular wing shape and a 9 feet wingspan, to our current final design, which has an 11 feet wingspan. And we decided to make the shape slightly tapered from a 12-inch root core to a 10-inch tip core. We decided to split the wing into 3 equal sections, which allows to have a 8-degree dihedral. We also decided to choose a NACA 441 airfoil for its high coefficient of lift to coefficient of drag ratio, which allows the plane to have a high rate of climb. To manufacture the plane, we decided to use a white low-density foam and light fiberglass to reduce the weight of the wing itself. We also use carbon fiber spars for its structural integrity, and bent steel tubes to attach wings together.
The tail, we went with a T-tail configuration, as you can see on the prototype right there. Went with that because it reduces the effectiveness of the turbulent prop vortices coming off the front by getting it up and away from those that turbulent section of air. Also gets the horizontal stabilizer further away from the ground during the belly landing to somewhat try and avoid any sort of collision there. And it increases the effectiveness of the rudder, which is extremely important because we don't have aileron control. Therefore, all turning is accomplished with the rudder. And going with that, 34% of that vertical surface is the rudder, which is quite a bit more than standard, just so we can have control authority. Same type of manufacturing with the fiberglass over white foam as the wing.
All right. With the fuselage, tail, and body all figured out, we then began trying to find the components that we would need to figure out how we would get this required distance parameter that we established at the beginning. We began by selecting our battery pack, which we selected the largest battery pack that we could get so that we could reach this distance goal. Once we selected the battery pack, we then went on and picked a propeller with a large diameter that could also fold because of the no landing gear. We then went and picked a motor that would achieve us the required thrust to lift this plane, and then finally an ESC with a rating that is higher than the maximum output rating of the motor. We verified our calculations using eCalc, and our calculations ended up being verified with our test flights. These are the results of some of our test flights. We reached a flight time of roughly an hour and 40 minutes, a distance of 88 miles, a cruise speed of 58, and a thrust rate to weight ratio of 0.43. And a thrust ratio of 0.2 is enough to actually lift up this plane.
So for the power system behind the plane, we were going for a really simplistic design such that if something broke or a part needed to be replaced, anyone in Zimbabwe could do it without a problem. They didn't need to be electrical engineers. So keeping that in mind, we tried to keep the wiring as simple as possible. Basically, we just have a standard LiPo battery as our main power source, goes through a current and voltage sensing board, which helps us monitor the status of those batteries such that the autopilot can perform fail-safes just in case something goes wrong with the batteries. And then also the main current load obviously is our motor, which is drawing most of the power from the LiPos. Just a little bit goes into the Pixhawk and runs the servos as well. On the first prototype, or the MK2, the first powered prototype, we were using these XT90 connectors. They're just a hobby connector. Unfortunately, they turned out to be kind of difficult to work with. They had to be soldered, and then also they didn't have good power distribution boards for them, so you had to solder like Y pieces in if you wanted to split the power to different loads. So then on the third prototype that we did, we switched to the Anderson power pole connectors, and these are very nice, easy to connect and easy to make. They don't require any soldering, just a crimp style connector, and they're also color codable. So to connect this the power system, basically all you have to do is connect the yellows to the yellows and the blues to the blues, and then once you have them all connected, you have this system connected correctly. So that just made it really simple for anyone off the street to be able to connect up the power for the plane. Also, they used power distribution boards instead of like parallel and Y adapters. This allows easy expansion for additional loads in the future, such as a satellite communication module, such that we can communicate with the plane when it's a very long distance away, and then also for the payload that we're expecting, basically the computer system behind the caller interaction. The system usually draws about 25 amps at cruise speed, and then 55 amps is the maximum that we've seen at takeoff. And this system is able to handle that current draw with no problems whatsoever.
And for the autonomous flight itself, we went with an open source solution, community backed, heavy community involvement. So if you ever have problems troubleshooting or need to know what's going on, you can reach out and someone will be there to answer it for you. So this helped us a lot with tweaking with the autopilot to make sure that it worked for Mark II and Mark III of the planes. The different flight modes that we use the Pixhawk and our ArduPilot is what we're using, the firmware. The different flight modes that ArduPilot provides to us would be manual, auto, RTL, FBW. A lot of these have specific uses. Manual basically for full RC control over the plane. Auto is when you'd be running a mission, say searching for the painted dogs. Also, hopefully in the future for an auto launch and auto land procedure so that the entire mission can be completely autonomous and we don't need someone who has RC capabilities flying the plane. One of these features is auto tune, one of these modes. And auto tune is needed in order to tune the PID controls for the autonomous flight. You can't actually fly in auto with the plane until these are done. Basically, you set it up there, throw it in the mode, and it will tune it so that the sensor information coming from the Pixhawk will be able to be mapped to the control surfaces for the plane. It also allows for a wide variety of control surface configurations for different planes. We have a rudder and elevator only, no surfaces on the wing itself, and it's actually very easy to put that in the software. Mission planning is relatively easy to do. Here's an example of it. This is actually Mission Planner, one of the user interfaces that we're using. The right side of the screen, you can see a bunch of waypoints listed out and a purple line showing the path of the craft. The waypoints, you can set them, it's a point and click, you bring the map up. So if you're in Zimbabwe, you bring the map up where you think the dogs are going to be, and you go, I want to survey this entire area, and you do about, it would be the 1.2 diameter swatches coming back and forth of these waypoints, and it will follow those paths, and hopefully when we get the ARPI installed, or the control computer on board, we can also redirect in mid-flight, go to the dog, get information, and redirect back to our old flight pattern.
So since we had the 65-foot takeoff and landing distance, we actually decided that a launcher would be the best way to accomplish this, since we may or may not have great takeoff areas. And since the landing gear, we decided it's best just to omit it. So after we decided that we wanted a launcher, we decided that we needed to choose the propulsion system for that. And to start off, we had pneumatic, folded bungee, and then a spring system. After looking at the pros and cons of the different ones, we decided that the bungee was going to be the way to go, since it proved to be the most cost-effective and easiest to transport. There are fewer specialized pieces. We just ended up going with a cradle system to keep the UAV off the launcher so that we could power it up fully before actually launching it, so that we wouldn't have a situation where we launched the UAV and then the UAV would come down because for some reason we didn't have enough power. We also decided to go with lumber for the frame, since it's cheap and easy to get, and since it's box shaped, it's also really easy to move over to extruded aluminum so that you can reduce weight by a lot at an increased cost.
So we're going to talk about just about our prototypes and our test flights. You can go ahead and click play there. So on the bottom you can see this is Mark 1. It was our very first glider prototype. This is Mark 2 flying here in its third flight. So takeoff and landings are all pretty easy with remote control. The rudder and elevator provide plenty of control for that. So we'll go around and I'll show you some like in-flight footage and things of that nature. So again, as Alex had mentioned, we have a fiberglass fuselage with the foam inside of it, and we were able to fly with our current batteries 23 miles in 19 minutes, which we were very happy with. And we will be flying with Mark III next week for longer distances there. So you can see us coming in for a landing here. Fantastic. And you can see the folding prop, how it's totally out of the way. Go ahead to the next slide there. So now you can see our final prototype here, painted nice. It has the new fiberglass fuselage, so we dropped all the foam weight. We're using a different foam weight now, so that makes it easier. And fast forward to the video. So again, in this one we had the newer fuselage, the same wing essentially, updated tail, and our larger batteries. So these are 22,000 milliamp hour batteries that should enable us to fly for the full 1.65 hours, and we'll be testing that next week to ensure that that is correct. But on our calculations, we should be able to fly 88 miles in 1.65 hours. Again, you can see the nice Pullman field. We're just rolling around here, and then we'll come in for a landing again. So flight characteristics overall were really good. We were really happy with our glider design. Made a lot of progress this semester, and we're really excited. Again, you can see the folding prop totally out of the way. We haven't had any issues with all of our 8 flights total on our airplanes. It's been very reliable. So for next steps for us, so for this semester, we want to increase the vertical stabilizer volume. So we had a little bit of a wagtail essentially when we went up and flew 2 days ago. So we want to reduce that with a little bit larger vertical tail. We want to have a better securing mechanism for the horizontal stabilizer. And then we want to complete our manufacturing and assembly, all of our guides, so that you can go from nothing to a full UAV with an instruction manual and make it very easy to work with. So for next semester, we want to improve the launch cradle attachment. We want to have a better sliding wing attachment, so the wings slide on nicely for detachable points there. We want to have an advanced autonomous flight control system, just very easy to work with, and that's what we're working with currently. Attain a dog collar for actual implementation and testing, make sure that system is good to go. Achieve auto takeoff and landing, and then ultimately fly without a transmitter for full autonomous flight. We'd like to thank the Painted Dog Research Trust with Gregory Ramson and Carrie Culp. They've been fantastic in this, helping with us and keeping this project going. We'd also like to thank Gene Jones, who is here with us today, and Kevin Kohler for their support in helping us through all of our design matrices and getting this as far as we were, and also Charles Pozeski for helping us with the 416 class. Thank you.